explore the fascinating mathematics that describes shortcuts through spacetime. A wormhole is a theoretical tunnel through spacetime that connects two distant points in the universe, creating a shortcut through space. Wormholes emerge from Einstein's field equations of general relativity. Einstein's field equations describe how matter and energy curve spacetime. The left side represents spacetime curvature, while the right side represents matter and energy. These equations tell us that massive objects curve spacetime, and this curvature is what we experience as gravity. Under extreme conditions, spacetime can curve so dramatically that it creates exotic geometries like wormholes. Here's a visualization of how a massive object curves spacetime. The grid lines bend downward, representing the warping of space around mass. The Schwarzschild solution describes spherically symmetric spacetime around a mass. The Schwarzschild metric describes the geometry of spacetime around a spherical mass. This is the starting point for understanding black holes and wormholes. The Schwarzschild radius Rs equals 2gm over c squared, defining the event horizon of a black hole. At the Schwarzschild radius, the escape velocity reaches the speed of light, creating a point of no return. A black hole has an event horizon at the Schwarzschild radius and a singularity at its center where spacetime curvature becomes infinite. In 1935, Einstein and Rosen discovered a theoretical bridge connecting two regions of spacetime. The Einstein-Rosen bridge metric describes a tunnel connecting two separate universes or distant regions of the same universe. The Einstein-Rosen bridge creates a tunnel through spacetime. However, this bridge is not traversable as it collapses before anything can pass through. In 1988, Morris and Thorne proposed a metric for a stable, traversable wormhole. The Morris-Thorne metric describes a wormhole with a throat of minimum radius b0 that remains open and traversable. The shape function b of L equals the square root of b0 squared plus L squared, describing how the wormhole throat expands. For the wormhole to remain stable and traversable, it requires exotic matter with negative energy density to hold it open. A traversable wormhole has a throat region filled with exotic matter that prevents collapse. This exotic matter violates the weak energy condition. Traversable wormholes require violation of classical energy conditions. The weak energy condition states that energy density ρ plus pressure P must be non-negative. Wormholes require this to be negative. This means the stress energy tensor contracted with any null vector must be negative, requiring exotic matter. Currently, no known forms of classical matter can produce the negative energy density required to stabilize a wormhole. Normal matter has positive energy density. Exotic matter requires negative energy density. We don't yet know if such matter exists in nature. Quantum mechanics provides a possible source of negative energy. The Casimir effect produces negative energy between two conducting plates separated by distance d. This is E equals negative pi squared h bar c over 720 d cubed. The Casimir effect shows that quantum vacuum fluctuations can produce measurable negative energy, though at extremely small scales. Between conducting plates, quantum vacuum fluctuations create a net negative energy density that pushes the plates together. Mathematical analysis reveals the conditions needed for wormhole stability. The flare-out condition requires dB over dL to be less than 1, ensuring the wormhole throat expands outward. At the throat, where L equals L0, the shape function B equals L0, defining the minimum radius. This graph shows the wormhole shape function. The throat is at the minimum, and the radius increases symmetrically on both sides, creating the characteristic tunnel shape. Wormholes could theoretically allow for time travel under certain conditions. Moving one wormhole mouth at velocity versus creates a time difference delta t between the mouths equal to versus times d over c squared. If properly configured, wormholes could create closed, time-like curves, paths through spacetime that loop back to their starting point in time. A closed time-like curve would allow travel to the past, creating potential paradoxes that physics must resolve. Let's summarize the key mathematical concepts behind wormholes. Einstein's field equations permit wormhole geometries as valid solutions to general relativity. Traversable wormholes require exotic matter with negative energy density to remain stable and open. Quantum mechanical effects like the Casimir effect demonstrate that negative energy is possible in principle. The mathematics shows that wormhole stability depends on satisfying precise geometric conditions like the flare-out requirement. If wormholes exist and can be manipulated, they could theoretically enable time travel through closed, time-like curves. The mathematics of wormholes brings together Einstein's relativity, quantum mechanics, exotic matter theory, stability analysis, and time travel implications into one fascinating framework.